Okay, today we are going to look at example number 2 and the solution of first order linear PDEs by method of characteristics, and we shall be following the procedure that we looked at in our example 1 that is in our previous lesson that we had. And our example 2 today is given by, the question is saying, solve 2 partial of u with respect to x plus 3 the partial of u with respect to y plus 8 u is equals to 0. Then the question is saying solve using the method of characteristics. Solve using the method of characteristics. So I want us to solve this one together. And therefore we are going to begin by looking at a general case of first order linear PDEs that we looked at in our previous lesson. So a general case of a first order linear PDE is given by a partial of u with respect to x plus b partial of u with respect to y plus cu is equals to 0. And then we said that the main things here, or the main values here, is the values of a and b, or rather the coefficient of the partial of u with respect to x, which is a, and the coefficient of u with respect to y, which is b. So in our equation here, we are going to identify the values of a and b. And when you look at this equation, the value of a here, the value of a is 2. The value of a is 2, and the value of b here is given as 3. So this is 3. So we have the values of a and b, where a is the coefficient of the partial of u with respect to x, and 3 is the coefficient of the partial of u with respect to y. So now we proceed. Now we are going to begin by writing our characteristic equation. We are going to begin by writing our characteristic equation. We're going to begin by writing our characteristic equation, and it is given by dy over dx is equals to b is supposed to be b over a. So our value of b is 3 over 2. Okay. Our value of dy and dx is 3 over 2. So now what we are going to do here, we are going to cross multiply. So this will multiply with this, and this will multiply with this. So we are going to have 2 dy is equals to 3 dx. 2 dy is equals to 3 dx. Then we take this 3 dx to this other side here. So it is going to be equal to 2 dy minus 3 dx. This will be equal to 0. That will be equal to 0. Then from there we are going to integrate. So we will integrate the whole of this one. I'm going to integrate the whole of that one. And when you integrate 2 with respect to y, we are going to get 2y minus, if we integrate 3 with respect to x, we will get 3x, and this will be equal to, when you integrate 0, it will be 0. Then plus a given constant, Then we can let our constant to be, let's say our constant is k. We can let this function 2y minus 3x to be a constant, like let's say k, like that. Then from there we are going to proceed to the second step, which is writing our characteristic curves. So we go to the characteristic curves. This is characteristic curves. So okay, we go to characteristic curves. Go to characteristic curves, and we said that we obtain characteristic curves from the characteristic constant that we have obtained from here. And as we said in our previous lesson, in characteristic curves, we introduce new variables, that is xi, and another variable that we call nu. So in this case, we are going to let this characteristic constant, that is 2y minus 3x, to be equal to either xi or nu, So in my case, I will let this function or this constant to be equal to nu. So therefore I will let this one to be equal to nu. So therefore nu will be equal to 2y minus 3x. So nu will be equal to 2y minus 3x. But remember, we are also supposed to have another function of xi. Okay? And for us to be able to come up with a function of the xi, we need to first of all differentiate this function partially, or this function of nu partially, with respect to both x and y. So we are going to obtain nu x, and we are also going to obtain nu y. So once we differentiate nu with respect to x partially, we are going to get negative 3. Of course, we consider the term that as x. Then when we differentiate nu with respect to y partially, we will get 2. Okay. Then with these two differential values for nu, we can be able to have our function for xi. So in this case, we can let our function to be any function so long as it will obey Jacobian rule and within the given values. So in this case, we can let our xi to be x. We can also let our xi to be y. We can also let our xi to be 2y plus 3x. We can also let our xi to be 3y plus 2x. So xi can take any of those functions. And for my case, I will let xi to be equal to x. Then as I have done here, I will also do the same here. So I will differentiate this xi partially with respect to x, and also differentiate the same function again partially with respect to y. And therefore I will get, when I differentiate this one partially with respect to s, I will get 1. And when I differentiate it again with respect to y, I will get 0. Because our xi function does not have any function, or does not have any term with y. So those are the values of, we have the value of nu x, nu y, xix, and xi y. So the next thing that we need to do, we need to test Jacobian rule. We need to test Jacobian rule, that is Jacobian of xi nu. Jacobian of xi nu. And Jacobian of xi nu should not be equal to 0. We said that Jacobian of xi nu should not be equal to 0. That is when we say that Jacobian rule is obeyed. And for us to test Jacobian rule, we are going to multiply xix by nu y. Then we subtract xiy by multiplied by nu x. So once we take xix, which is 1, multiplied by nu y, which is 2, we're going to get 2, because 2 times 1 is 2. Then, when we take xiy, which is 0, multiplied by nu x, it will be 0. And therefore, 2 minus 0 will be equal to 2. And therefore, Jacobian rule, or Jacobian of xi nu, is not equal to 0. And hence, Jacobian rule is obeyed. Hence, Jacobian rule is obeyed. Since we have obtained the values of nu x, nu y, xix and xiy, then we need to obtain the values of the partial of u with respect to x and the partial of u with respect to y. And for us to obtain these values, as we said in our previous lesson, we differentiate u partially with respect to x in terms of the new variables xi and nu. So we are going to proceed by obtaining the value of the partial of u with respect to x in terms of xi and nu. And so the partial of u with respect to x will be equal to, so we differentiate this u partially with respect to x, but in terms of xi, okay, multiplied by the partial of xi with respect to x. But instead of writing the partial of xi with respect to x, we said that we will be writing xi x. Then plus the partial of u with respect to nu. So this will be dot nu x, instead of writing the partial of nu with respect to x, like that. Then remember that we have already obtained the values of nu x and the value of xix. So we are going to substitute them here. So that now our partial of u with respect to x will be equal to the value of xix is 1. So it will be the partial of u with respect to xi. Okay. Then the value of nu x is negative 3. That one we have already seen. We've already seen that the value of nu x is negative 3, and therefore it will be minus 3, the partial of u with respect to nu. So that is the value of the partial of u with respect to x. That is the value of u, the value of the partial of u with respect to x in terms of nu and xi. That is our new, which is our new variables. Now, having obtained the partial of u with respect to x, we also proceed to obtain the partial of u with respect to y in terms of xi and nu. Therefore, we are going to have the partial of u with respect to y will be equal to the partial of u with respect to, it will be xi. Okay. Then instead of writing the partial of xi with respect to the value of the partial of xi with respect to y, we are going to write xi y, then plus the partial of u with respect to nu. So this one will be dot nu y. That is, instead of writing the partial of nu with respect to y, we just write nu y. Okay. But then remember, we have obtained the value of xiy, the value of xiy, which is 0, and the value of nu y, which is 2. So we are going to substitute them. We are going to substitute them in our case here. So this will be, we have already seen that the value of xiy is 0. So this will be 0. And the value of nu y, we have seen it is 2. The value of nu y is 2. So we are going to substitute 2 there. So this will be 0, and 0 times n number is 0. So this will be positive 2. Well, that is for nu y is 2. Then partial u with respect to nu y. This is the partial of u with respect to y. So this is the value of the partial of u with respect to y in terms of nu, because xi has vanished. Then, since we have obtained the value, the partial of u with respect to x and the partial of u with respect to y, we are going to make substitutions in our given question. We are going to substitute them in the given PDE. And remember that our given PDE is given as 2, the partial of u with respect to x, plus 3, the partial of u with respect to y, plus 8u is equals to 0. So we are going to substitute the values of the partial of u with respect to x and the partial of u with respect to y. And we have already obtained them. We obtained the partial of u with respect to x as this function. This is the partial of u with respect to x, the whole of this function. Then we have the partial of u with respect to y, which is this function. So those are the functions that we are going to substitute in our general PDE, or the question that we are given. Therefore, we are going to have 2 into brackets the partial of u with respect to x. So we go back to where we have the partial of u with respect to x, and it is the partial of u with respect to xi minus 3, the partial of u with respect to nu, like that. That is the partial of u with respect to x. We have substituted its value here. Then plus 3, the partial of u with respect to y, which is here. The partial of u with respect to y is here, and we are going to substitute it here. So I'm going to have 2, the partial of u with respect to nu, like that. Then plus 8u, which is here. 8u, it is already here. That is 8u, okay, is equals to 0. So that is what we have after making substitutions of the values of the partial of u with respect to x and the partial of u with respect to y. So we are going to proceed by opening the brackets. So this will be 2 times this one will be 2, the partial of u with respect to xi, minus 3 times 2 is 6, the partial of u with respect to nu, 3 times 2 is 6, so it will be plus 6, the partial of u with respect to nu, then plus 8u is equals to 0. So we have opened the brackets. We have opened the brackets. Okay. So now from there, some terms will cancel one another. Minus 6 partial of u with respect to nu will cancel with 6 partial of u with respect to nu. Of course, this one minus this one is 0. So they will cancel. Once they cancel, we are going to remain with, once they cancel out, we are going to remain with 2, the partial of u with respect to xi plus 8u is equals to 0. So we are going to remain with 2 the partial of u with respect to xi plus 8u is equals to 0. And of course we can make the coefficient of the partial of u with respect to xi to be 1. So we are going to divide the room by 2. And once we divide the room by 2, we are going to get the partial of u with respect to xi, the partial of u with respect to xi. Once we divide 8 by 2, it will be 4. So we are going to have 4u is equals to 0. So this is our function, partial u with respect to xi plus 4u is equals to 0, where the coefficient of the partial of u with respect to xi is 1. So this is the canonical form of the PDE. This is the canonical form. This is the canonical form of our PDE. This is the canonical form of our PDE. Then, with this canonical form of our PDE, that is the partial of u with respect to xi plus 4u is equals to 0, we are going to find now the value of u, which is our independent variable, by integrating the function. And we integrate this function by use of the method of the integrating factor. We solve for u by integrating the function using the method of integrating factor, and we said that integrating factor is given by exponential the integral p with respect to the independent variable of the function which we are solving. And in this case, we are solving a function with the independent variable xi. Okay, so we are going to obtain our integrating factor method. Our integrating factor. Sorry. Therefore, our integrating factor will be equal to exponential the integral of p, and we said that the coefficient of u, when the coefficient of the partial of u with respect to xi is 1, is the value of p, and the coefficient of u here is 4. So the value of p here is 4. So this will be 4 then with respect to xi. So it will be 4 with respect to xi. So this will simplify to exponential 4xi. So this will be our integrating factor. So our integrating factor is exponential 4xi. Okay. Then we said using the method of integrating factor, u will be equal to using the method of integrating factor, u will be equal to, we said that we usually take 1 over the integrating factor, the integral of, we usually take 1 over the integrating factor, the integral of g of xy, the given function at the equal sign here, then multiply by the integrating factor with respect to the given independent variable that we are operating with, which is xi, like that. That is just a general case of how we obtain the value of u using the method of integrating factor. Then, therefore, we are going to substitute our integrating factor and g of xy in this case. So u will be equal to 1 over our integrating factor is exponential for xi, the integral of the function here given at the equal sign is 0. So we are going to substitute 0 where we have g of xy. So it will be 0 multiplied by our integrating factor, which is exponential for xi with respect to xi. It is, of course, it is depending on the independent variable that we are operating with in obtaining the value of u. Okay. Then from there, We can take this one to the other side by multiplying the room by exponential. We need to multiply the room by exponential 4xi. So once we multiply the room by exponential 4xi, we are going to have u dot exponential 4xi is equals to, now this will be 0 because 0 times this one will be 0, so it will be 0. Okay, it will be 0 with respect to xi. Then of course we are integrating that one. Okay, now when we integrate 0 we get 0. When we integrate 0 we get 0, and therefore we are going to have u dot exponential for xi will be equal to 0. Of course, when we integrate, we must always have plus a constant. So I'm going to have a constant which will be a function. If we are dealing with respect to x and we enter our new variables as xi and nu, and here we are dealing with respect to xi, so the constant will be a function of nu. The constant will be a function of nu, like that. So the constant will be a function of nu like that. Then of course we take this one to this other side again. So it will be u will be equal to, we divide the room by exponential 4xi. So once we divide the room by exponential 4xi, we are going to have u is equals to exponential 4xi. So it will be negative. So instead of writing 1 over exponential 4xi, we will write exponential negative 4xi. Then multiply by g of nu, like that. Multiplying by g of nu, like that. Now, but remember that our original variables were x and y, but not nu. Now, recalling that we let our xi to be equal to x. Then we also let our nu, recalling that we let our xi, we already let our xi to be x, and we also let our nu to be 2y to be 2y minus 3x. Okay, we let our xix to be x and nu to be 2y minus 3x. We are going to substitute them. So where there is xi, you put x, and where there is nu, we put 2y minus 3x. Therefore, our u will be equal to exponential negative 4. Where there is xi, we put x, multiplying by g of nu, and nu is 2y minus 3x. Okay, so once we substitute like that, we have u is equals to exponential negative 4x multiplied by g of 2y minus 3x. So this is the solution that we were looking for. So this is our solution of the PDE. This is the solution of the PDE. So thank you so much for watching. Please, if you have not subscribed, subscribe, comment, like, and also share to your friends, and God will bless you. Thank you so much.